All right, let's dive right in. Today we're talking about something pretty critical, the first few hours in the life of a brand new oil and gas well. It's a process called surface testing. And when you look at a setup like this, you can really see what we're talking about. This is where the raw, chaotic energy from deep underground first gets tamed by some serious engineering. So, what really goes on when you first open the taps on a new well? I mean, it's not like turning on a faucet in your kitchen. Not even close. It's this incredibly complex, carefully choreographed dance that determines pretty much everything, from how safe the operation is to how profitable the whole project will be. The best way to picture this whole thing is to imagine a high-stakes sorting facility and a state-of-the-art science lab all rolled into one. And the kicker? The whole setup is temporary, just popped up right there on site. Its number one job is to safely sort out that chaotic mix of oil, gas, and water that's whirring up from the ground, all while figuring out exactly what kind of prize you've found. Okay, so to really wrap our heads around this pop-up factory, we need to understand its four core missions. Think of these as the fundamental why behind every single valve, pipe, and tank we're about to look at. At its core, surface testing is just that, a temporary but incredibly well-engineered package of equipment. Its entire reason for being is to safely manage and separate that initial flow so you can get the critical data you need. So remember these three words: safety, separation, and analysis. They are the name of the game. And here they are, those four missions laid out perfectly. First, you have to control that immense pressure. Then you've got to sort that mix of gas, oil, and water. After that, you need to grab good, clean samples for the lab. And finally, you have to dispose of everything responsibly. We're going to tackle these one by one, starting with the biggest one of all, controlling the pressure. This is it, the first point of contact. This is where the raw, untamed power of the well meets human engineering head-on. Every single component in this first stage is designed for one primary purpose: to safely tame the incredible pressure coming from deep inside the earth. And this is the flow head. It's basically a temporary version of what's called a Christmas tree on a permanent well, and it sits right on top. So let's walk through its four key valves. First, you have the master valve. Think of that as the ultimate off switch. Then there's the swab valve, which gives you access to get tools down hole. The main tap that controls the flow? Well, that's the flow valve, and it is absolutely critical that it's linked into the automated safety systems. And last, you got the kill valve, which is kind of a reverse switch for emergencies, letting crews pump fluids down into the well to control it. So once the flow head has the raw flow contained, the choke manifold steps in. It's kind of like the nozzle on a pressure washer. It lets you fine-tune everything. During the initial cleanup phase, you'd use a variable choke, so you can adjust the flow without shutting things down. But for the official test, the one that really determines the well's value, you switch to a fixed choke. This uses these precisely sized little discs, they call them beans, to guarantee an exact, repeatable flow rate. And that precision is absolutely crucial for the financial side of things. Okay, pressure's been tamed. Now we can get into the science lab phase of this whole operation. This is where we start to break down that raw stream of fluid into its valuable components. Now, the first stop in our science lab might seem a little weird. It's a heater. You're probably thinking, why on earth would you heat up oil and gas? Well, it turns out this heater is a crucial peacemaker in the process. It doesn't just warm things up, it prevents some major problems that could bring the entire test to a screeching halt. So why do you need a heater? Three huge reasons. First, when high-pressure gas expands really fast through that choke, it gets incredibly cold, cold enough to form these ice-like blockages called hydrates. The heater stops that from happening. Second, it warms up any thick, gunky oil, making it less viscous so it flows and separates easier. And third, it helps break up those really stubborn mixtures of oil and water, what we call emulsions. Honestly, without the heater, the next step would be nearly impossible. With the flow all heated up and stable, it's time for the main event, the test separator. This is the true heart of the whole testing package. This is the sorting facility. Inside this big vessel, a combination of gravity and some really clever internal mechanics separates that stream into three distinct layers. You get gas on top, oil in the middle, and water down at the bottom. This is the moment we get our first really accurate measurements of what this well can do. So, we've controlled it and we've sorted it. The final steps are to double-check our measurements and then dispose of all these fluids responsibly. This is all about good accounting and good environmental stewardship. From the separator, the oil and water flow into holding tanks, which act as a final quality check to calibrate the meters. But not all tanks are created equal, not by a long shot.
A standard gauge tank just vents to the atmosphere. But if there's any risk of hazardous gas, like hydrogen sulfide H2S, a pressurized surge tank is absolutely non-negotiable. It's designed to contain those dangerous gases, which makes the choice between them a life or death safety decision.
So what happens to all this stuff we just produced? Well, the gas is sent to a flare, and the oil is often burned using specialized equipment. And this is a really key point about modern operations. These aren't just smoky pits. As it says here, they use compressed air to atomize the oil into a fine mist. This ensures a remarkably clean and efficient burn, which really minimizes the environmental footprint of the whole test. We've walked through the whole process now, but underneath it all, there's one final system. It's the silent, ever-vigilant guardian that makes sure if anything at all goes wrong, the situation is contained instantly. The entire safety philosophy here really boils down to this one number, 2. At all times, there must be at least 2 independent barriers that can hold back the well's pressure. This could be a valve way down hole and a valve on the surface. Redundancy is absolutely everything. And here's how that redundancy works in just a split second. Let's walk through the sequence for the Emergency Shutdown System, or ESD. 1. A sensor detects a hazard, say a sudden pressure spike. 2. The ESD system is instantly and automatically triggered. 3 and 4. That signal engages hydraulic power to slam the critical valves on the flow head shut. And 5. The well is secured. This entire chain reaction happens in moments, far, far faster than any human could possibly react. So, from controlling immense pressure to the fine science of separation and the fail-safe systems that guard it all, surface testing is really a masterclass in temporary, high-stakes engineering. It's the critical first step that defines the future of a well. And that leaves us with a really compelling question for the future, doesn't it? As automation and AI get more and more integrated, just how much smarter and safer can a process like this become?